Today I'll talk about Gauss-Jordan Elimination Method. Here I'll give the complete row reduction solution. So here is the system of linear equations. Three equations are there. By using Gauss-Jordan Elimination Method, I'll find out x, y and z. So here is the key concept. So first convert system to reduce row echelon form, that is RREF, and then make all pivots 1 and eliminate above and row. So first I'll make augmented matrix. So here is the augmented matrix. From this equation I make the augmented matrix, initial augmented matrix, and our goal will be transform that augmented matrix to that the left hand side unit matrix, and then when we will do the operation, so that the right hand side that constant matrix will change and that will give the solution. So for that, first I am making that second row first element and third row first element 0. So for that I have to do that second row operation and third row operation. So here is the row operation. So R2 minus 2R1, that will give new R2, and R3 minus 3R1, that will give new R3. By doing that operation, I'll make that second row first element and third row first element will be 0. So here if I do the operation, so R2 minus 2R1, so that will give 0 minus 3 minus 3 minus 1. So here R2 is 2 1 minus 1 3 minus 2 into that R1. R1 is 1 2 1 2. So if I do that operation, we'll get 0 minus 3 minus 3 minus 1. And similarly, if I do that R3 operation, so R3 minus 3 R1, so R3 is 3 minus 1 2 1 minus 3 R1 1 2 1 2. So after doing that, after doing the calculation, new R3 will be 0 minus 7 minus 1 minus 5. So now if I plug that new R2 and R3, so new matrix will be like that: 1 2 1 2, 0 minus 3 minus 3 minus 1, 0 minus 7 minus 1 minus 5. Now I am going to make this that first row second element 0. So for then again I have to do that row operation of first row operation. So here the eliminate above second pivot. So here first row operation, R1 minus 2 R2, that will give R1, new R1. So new R1 is nothing but old R1 1 2 1 2 minus 2 into R2. So if I do that operation, then new R1 will be 1 0 minus 1 4 by 3. So if I plug that new R1, so new matrix will be 1 0 minus 1 by 4 by 3, 0 1 1 1 by 3, 0 minus 7 minus 1 minus 5. Now next step, so minus 7 means third row second element I'll make 0. So for that I'll do this operation. So R3, new R3 will be R3 plus 7 R2. So here my old R3 is 0 minus 7 minus 1 minus 5. So minus 7 I'll going to make 0. So R3 plus 7 R2. If I do that operation, so here that new R3 will be 0 0 6 minus 8 by 3. If I plug that new R3, so now my matrix will be 1 0 minus 1 4 by 3, 0 1 1 1 by 3, 0 0 6 minus 8 by 3. So now here I am going to normalize third row. So I am going to make that in the element third row third element 1. Okay, so our target is all diagonal element should be 1. So for that, here is the normalized third row. So I am doing R3 divided by 6, so that will give new R3. So new R3 will be 0 0 1 4 by 9. After doing that operation, we will get that. Now if I plug that, so that will be 1 0 minus 1 4 by 3, 0 1 1 and 0 0 1 minus 4 by 9. So now next step is first row third column third element, and second row third element, I'm going to make 0. So then this matrix will be unit matrix. So for that I'm going to do that operation. So new R1 I'll make, so that will be, if I do what will be the operation, so that will be R1 plus R3, so that will give new R1, and R2 minus R3, so old R2 minus R3, so that will give new R2. So old R1 is 1 0 minus 1 4 by 3 plus R2 0 0 1 minus 4 by 9, so that will give new R1, so that is 1 0 0 8 by 9, and new R2, so that is R2 minus R3, so old R2 is 0 1 1 1 by 3 minus 0 0 1 minus 4 by 9. So if I subtract R2 minus R3, so that will give R2, so that will be 0 1 0 7 by 9. So if I plug new R1 and new R2, so that will be 1 0 0 0 1 0 0 0 1, and that constant matrix become 8 by 9 7 by 9 4 by 9. So that constant matrix, so this one will be my solution. So now here, so final solution, okay, so and this is actually called reduced row echelon form, so that is RREF, so reduced row echelon form. So from that, so solution is from row 1 x is 8 by 9, so and from row 2 y is 7 by 9, and from row 3 z is equal to minus 4 by 9. Now if I write in the decimal form, so x will be 8 by 9 is just nothing but 0.889, y will be 0.778, and z will be minus 0.444. Now after getting that value, I have to check whether these values are correct or not. So for that, so okay, the system has a unique solution, that is x is equal to 8 by 9, y is equal to 7 by 9, z is equal to minus 4 by 9. Now I have to verify that. So verification, so original system of equation is x plus 2y plus z is equal to 2, 2x plus y minus z is equal to 3, and 3x minus y plus 2z is equal to 1. Now I got that x, y and z value, and I will plug whether left is equal to right. If I get left is equal to right, so that whatever solution I get, that will be correct. So first verify equation 1. So I am plugging x 8 by 9, 2 into y 7 by 9 plus z minus 4 by 9. If I do the operation, so I'll get that left hand side is equal to 2. So that is the verified. And next second equation, so that is 2x plus y minus z is equal to 3. Again if I plug that x, y, z value, so that left hand side is equal to 3. So 3 is equal to 3 means left hand side equal to right hand side. Similarly, if I do that verify the equation 3, so 3x minus y plus 2z is equal to, again if I plug x, y and z, so I'll get 1. So left hand side is equal to right hand side. So finally, so verification complete, all equations are satisfied by this x is equal to 8 by 9, y is equal to 7 by 9, and z is equal to 4 by 9. So that solution is verified to be correct, and solution is x is equal to 8 by 9, y is equal to 7 by 9, and z is equal to minus 4 by 9. That's it. Thank you.